Hi student and audience, this is the third lecture on this topic, and in this lecture we will discuss the optocoupler and the TL431 functional basics of this optocoupler, and this is called operational transconductance amplifier, TL431. Okay. This story is very easy. And maybe you think this is not directly related with power electronics, but the knowledge about this is also important. Okay, so this is the essential step to transfer your knowledge about this power electronics to the working hardware. Eventually, you need to build the working hardware converter. Then you should know the basic things about this optocoupler and this operational transconductance amplifier. Okay, this is the schematic diagram of our converter you are dealing with, and this part is the IC NCP 1230. That chip is from ON Semiconductor. People call it ON Semi. Previously, I told you something else. Some strange company. I checked that out. This device is coming from the ON Semiconductor, and this is the photo of the optocoupler. So this is a 4-terminal device. So this is the infrared diode, and this is the photo transistor. Two devices in one package, and this is the operational transconductance amplifier. Brand name is TL431, and actually this is a 3-terminal device. So it looks like this, very small. It looks like transistor. It's not a transistor. Name is TL431. This is very cheap. Okay. Usually this optocoupler and this TL431 is used as a combination. So this is the cheap or very cost-effective solution for this type of application. For the home electronics, industrial electronics, the cost is the prime concern of the manufacturer. So they are using this cheap solution, but this is acceptable, and this is connected to this bias voltage, VDD, and this part is voltage feedback circuit, and actually this becomes the 2-pole 1-0 compensation. All right. So first we deal with this optocoupler. So this is the structure of optocoupler. Optocoupler this is the infrared diode. This is the photo transistor. And this is the parasitic capacitance built in this photo transistor. So this CJ is large compared to the conventional regular transistor. I'll explain the reason why. That can be a kind of problem when using this device. And this is the structure of this device. Two devices in one package, and there is a dome. This one is LED, light emitting diode. This one is photo transistor. So there is a dome. Okay, the shape is ellipse. So this is called the elliptical dome. So with some current, photon is coming out. It goes this direction and reflected to here, and it reaches the base area of this transistor, photo transistor. So to have the maximum efficiency, light efficiency of the photons, there is some structure, elliptical structure. So this maximizes the receiving of the photon from this source. Okay, and there is a distance, and this is a 4-terminal device. Optical coupling between gallium arsenide infrared light emitting diode and the silicon-based photo transistor, and the two devices in one package. Okay, so transmission of, it's not a current. It's not a current. It is a current, but more appropriate wording is feedback isolation, and the capacity of isolation is very good. So kilovolt can be insulated in between, and a substantial large is more appropriate word. A large parasitic capacitance CJ between collector and emitter of this phototransistor. Okay, so this is very large compared to other regular transistor. Okay, so this can be problem some applications, and some applications is not a problem. Okay, probably for this flyback converter, this CJ is not a problem, but some the other applications, some fast telecommunication, something like that, this can be a problem. Okay, large C delays the signal, and system becomes slow with this large C. But for our case, that won't be a problem. Okay, and again, this is the same thing. Okay, we discussed the circuit operation of this bias circuit, and if you remember that, okay, first this VCE is determined, or not this one, VCE is first determined by the PWM waveform for the required duty ratio. Okay, when this VCE is determined with some bias circuit, IT is determined, then IT is determined, ID is finally determined with this CTR. Okay, so CTR is a very important parameter, but CTR cannot be measured accurately, and there is some huge tolerance of the value. Okay, so you should consider that, or you should carefully evaluate the CTR of your device at your operational point. Okay, so this is the curve, this is the forward column, and this is the CTR. CTR is the ratio between this and this. Okay, so this varies with VCE. The bias voltage of this photo transistor is directly affecting this ratio, transfer ratio. So this is the fixed, and N is related with some number, related with the PN junction. I don't know the details about that, but this is fixed, right? Everything is fixed, and this CTR is changing as the function of the ID. Okay, so ID is varying from here to there, then CTR you change. One example with this much. Okay, and even worse, the CTR highly depends on this sample by sample, right? So there is a huge, large uncertainty in value of the CTR. Okay, but CTR is an important parameter for the isolate feedback controller. An important design parameter for isolate feedback controller for color mode control, and here we need to measure this one. CTR should be measured. We cannot trust this data. Okay, so it's better to measure this, right? We'll explain how to measure this, and finding out this value is the CTR and ID is rather tricky. Okay, so we know this is the first fixed, right? So this is there are three curves, but this is all three curves belongs to one device. Okay, this curve varies device by sample. So we expand out this part, and we select, for example, sample B, but even for the sample B, depending on this VCE value, there are three different curves. Okay, so let me explain in this way. Okay, first steady state value of the VCE is determined from the required duty ratio for the desired out voltage. So this is the fixed, right? This is the same as the control voltage for most cases. And IT is determined, you have some bias circuit here. So IT is determined here. So you know this VCE and IT. You don't know this one, and you don't have any idea about CTR. Okay, so you need to find out CTR from the given data. So what you know is this voltage. So VC 1, 2, 3, you select one. Okay, maybe you select one, or the closest one. Okay, assume your case belongs to this curve. So you have this curve and this axis, and the equation is this one. CTR is IT divided by ID. That means, suppose you have ID, then you know this, then the ratio between CTR. Okay, so this is very similar to the equation of Y equals constant K times X. X is ID, Y is CTR. Okay, so this is known. So from these three curves, you select this one because IT is known, VC is known. So you select this one and this curve. So you draw this circuit. This is the generated from this equation. Okay, this is the simple equation. Then you have a crossing point with this one. Then this is the operating point. Okay, so operating point Q1 is determined. Then this value becomes CTR of 0.65, something like that. And this value is ID. Okay, so with this ID is determined, CTR is determined. Okay, so if this changes, then you need to use this one, this curve or this curve. If the ID is changes, the VT this K IT changes, maybe operating point will move around like this. This is for the case of IT1. The IT1, and this increased or decreased, then this point will move here. Then CTR varies and ID varies. Okay, so this value and this value from the bias circuit, that information you determine CTR and ID. Okay, that is the basis for the design of the remaining part of this bias circuit. So steady state value of VCE and IT are predetermined by the PWM waveforms, and with this curve, you find out this using this equation, and you find out this Q point. Then ID is determined. Everything is determined. So this curve gotta be very accurate. Otherwise, what you are doing is just garbage in, garbage out. Okay, but the manufacturer, they don't have good data for this. Okay, so there is some uncertainty in the optocoupler parameter. So your design should incorporate some tolerance of this parameter. Later on, you will see this CTR and even the parasitic capacitance CJ becomes the critical parameter determining pulse and zero of your compensation. Okay, so that is the bad thing about this using this optocoupler. Data is not reliable, and your compensation design can be different with some tolerance. So you should consider that in your mind when you are using this. Okay, and something about the parasitic capacitance of optocoupler. So this is the parasitic capacitance is large. Okay, the reason for this is you want to have the effective photon transmission. So CTR, larger CTR is desired. Then you want to have a wide base area. This is the physical base area. So this becomes wide. Then parasitic capacitance between this becomes large. Okay. So CB, parasitic capacitance, junction capacitance between collector and the base is larger than normal transistor, and this one is amplified when you are seeing here. Okay, so CJ is this actually the parasitic capacitance between collector and the emitter plus times beta. Beta is current ratio between base current and collect current. So usually beta is large, 100, 200, something like that. So the CJ is this one plus this one magnified by this. This effect is called Miller effect. Okay. I don't know, Miller, you know, the Miller. Name of the beer, Miller. Okay. So name comes from him, I don't know. And in the electronics, maybe you heard the Miller integrator, maybe same guy, okay? Maybe same guy. This is called the Miller effect, and he named the Miller integrator, which is a simple integrator. So value of this is this one, order of nanofarad. Usually parasitic resistance is order of picofarad. So 10 times larger than normal value. For some applications which requires fast response of this optocoupler, okay, because of that the people is not using this, they are using something else, something expensive. But this is the cheap, and this is a fine for our application, for the flyback converter, for consumer electronics. So this is a very popular choice. Okay. And again, this CJ needed to be experimentally measured. Okay. So this is the simplified circuit diagram of to measure the value of the parasitic capacitance CJ. This is the effective parasitic capacitance seen by this in collector and emitter terminal. Okay, so this is the setup. Okay, and this is the AC signal. So AC signal is coupled with this. So AC is passing through this, and this is the DC and DC, and IT should be the same DC value for same edge value at your application circuit. Okay, so you need to control this. So this IT is the same as the real IT in your application circuit. Okay, then you measure frequency response of this, and the CJ and this RT forms a low frequency, a pole, single pole. So this pole, there is a pole. This is the DC value, and there is a 3 dB dip here, and the slope is minus 20 dB per decade. So this is experimental data. So we know there is a single pole, and the single pole is coming from combination of this and this, and from this you observe this frequency, and FP is given by this, and with this data you estimate CJ. Okay, so this is measurement. Okay, maybe reasonable measurement. So this should be measured. So there is anyway there is uncertainty between CTR and the CJ in optocoupler. Okay, that can be a problem. And this VCT and VST is small signal variable sinusoidal component on the top of DC value of this. Okay, so you are measuring this AC in, AC out. Then from this curve, okay, you need some equipment to measure this continuous curve, or you use the simple oscillator. Then you will simple scope. Then you will have dot. Okay, discrete data point. Then from that point, you obtain this and estimate this corner frequency, 3 dB frequency. All right. Okay. Another one is about this gallium SNID diode, IR diode. Okay. This is the typical curve. This is the forward voltage. This is the forward current. Okay. So there are many curves, depends on this column. But this is very sensitive to everything, all right? So select one. So maybe this is this one, 25 degree in centigrade, okay? Then first, people usually approximate this as a line segment combined like this, piecewise line segment. This is the approximation of this nonlinear curve, okay? Then this voltage becomes VDB. This is the VDF. I'm sorry, DF. And this slope, constant slope for this particular case, okay? Actually, you are predicting this approximately with this piecewise linear line segment, and the slope of this one is this RD, 1 over RD, this VDF, and you have ideal diode, okay, to have unidirectional current flow. But this is the piecewise linear model. This is the DC model. But what you are really interested in is AC model. AC model is just the slope of this curve. This curve, this is long. This red curve is long. Curve is something like this, okay? Very similar to this, all right? The slope is dimension is conductance, which is 1 over resistance RB. So RB is small signal resistance. So for the AC analysis or compensation design, you must use this small signal resistance. Okay, you have learned this in electronics in your sophomore class. Okay, so but still, that knowledge is necessary here. And I made a mistake. I need one inverse of this. Okay, so numerator and the denominator is swapped here. So I need to swap again. And typically this value is this one, 50 ohm. So knowing this value is very important. So when you are analyzing or designing the compensation circuit, this works as a resistor. So you should consider this later. Okay, but this you have this small one. So small one is better. 0 is ideal. 0 is this one, this vertical line. So at this region, this RD is large. So you have small RD. The ID should be larger than 1 milliamp, okay? And it should be much larger than 1 milliamp, okay? So there is a good reason for this other than this, okay? I'll explain that later. A, not sufficiently small ID effect, small signal transfer function of feedback circuit, and it also badly influence the operation of TL431, operational transconductance amplifier, okay? Right, so this is about the optocoupler, and the next one is this transconductance operational amplifier, TL431, okay? What is a transconductance amplifier? Why we call it transconductance operational amplifier? I'll explain that here, okay? This is the device. So TL431 is this one plus this one. Actually, this is actual transconductance amplifier plus a voltage reference. So it has voltage reference fixed at 2.5 volt. So they are coming as a package. So everything here is this one. Okay, let me redraw this. TL431 is this one, including this reference voltage. This is the 3-terminal device. 1 terminal, this is called anode, cathode, and reference, something like that. All right. What is the transconductance amplifier? Input of transconductance amplifier is voltage, and output of transconductance amplifier is current. Okay, so if you change here, this is AC component of our voltage. It goes here, something like that, and it changes this current, right? This current. Then this current is transmitted to this, and this current is used as the feedback signal. Okay. If you connect the one resistor here, so for some reason, then you obtain this voltage. Voltage amplifier, but here we are using this as the feedback signal. Okay, so output means it's not simply located at output. That's the meaning of the output. Output is the signal we are using for our purpose. You are extracting this current, and the current is transmitted through this optocoupler and used as the feedback signal. So input is voltage and output is current. Of course, there is an output voltage here if you connect this, but it's not the output. It only appears at the output port of this device, but it's not the output signal. Okay, you understand this, right? And this is also called shunt regulator. The name shunt regulator comes from the structure of the feedback amplifier. Maybe you heard the term shunt sampling series mixing, something like that. Okay, when you are extracting out voltage for the feedback amplifier, not this one, audio amplifier, that is called the shunt sampling. So we are sampling this current, and you are making use of that signal as this for the negative feedback mechanism. In that sense, this device is also called shunt regulator. Okay, understand this? All right. So OTA is standard terminology. Operational transconductance amplifier is very important device. Some application. Okay, for the IC people, they know where. Okay, I'm just teaching this in my electronics course. Okay, so I don't have any deep knowledge about this, but I know what is the meaning of transconductance amplifier. Okay, so one amplifier can be a voltage amplifier or a transconductance amplifier. This is called transconductance amplifier. For this purpose, it has some special structure suited for this kind of application. Okay. This is the internal diagram of this TL431 operational transconductance amplifier. The order has been changed. Operational trans amplifier. Okay, so the very simple device. Okay, but this is a very smart device. So we only have 3 terminal, anode, reference. Okay, this is the difference from the reference voltage. This is the maybe non-inverting input voltage. Okay, and this is cathode. Okay, and you take a look at this. There should be some bias. Okay, there is no energy source here. That is connected from the outside through this terminal. So VK is here and IK is coming in. Then VK is going through this, turn on this, and going through this, turn on this. This is the diode connected to BJT. So this becomes one input voltage. Okay, this is non-inverting voltage plus. Okay, and this is the voltage reference. It's called the band gap reference. Band gap reference has some property, very desirable property. It compensates the dependence of temperature. So this is the temperature compensated transconductance amplifier is here. So same as connecting this port at this voltage source, which is very stable, not changing with temperature. Okay, so this inverting terminal non-inverting terminal here. And this is just the protection. Okay, diode is, this voltage cannot be negative because of this. And there is this capacitor, it's called the compensation capacitor. So every operational amplifier has compensation capacitor. Purpose of that is with this. So this is a transconductance amplifier. So input is VR AC input, and output is IK AC IK, and you want to have infinite gain for all frequencies. That is impossible. Okay, so if you do not do anything about this characteristic is very strange. Okay, so you cannot predict this. Then if you put this one, this becomes a false diode. It shows false diode characteristics, something like that. So this is the pole. This pole frequency is determined by this capacitor, and the distance seen by this port, combination of this and this somehow. Okay, so this is the compensation cap, very important for the operational amplifier. And the output stage is this one. This is this kind of configuration is called Darlington pair. Darlington is the name of the guy, very famous in electronics. I remember when he died, maybe 20 years ago. I was teaching electronics. I heard the news he died. Okay? He is a very famous one. And this is the Darlington pair. So this is the, some cascade connection of the two BJT. Then it provides very good characteristics. One apparent thing is the effective beta. From here to there is multiplication of two betas, one beta followed by one beta. Okay, so it has this kind of structure, and the collector is open. Collector is not connected here. It is stand alone. So this is called open collector circuit. Okay. For the transconductance amplifier, there should be open collector structure. Okay. And this works as inverting, not inverter, inverting circuit. It's not changing the sign of the signal. Okay. There is not meaning of inverting. Inverting means if this voltage increase, this voltage decrease. If this voltage here decrease and this voltage increase, there is the inverting action. Okay, not changing sign of a signal, it's changing the direction of increase or decrease. That is called inverting. Okay, so we have inverter here, right? So it has inverter and this compensation cap to have these characteristics. And so to proper operation of everything, you should have some final voltage and some current coming in from the cathode terminal. If this voltage becomes too small, this current becomes too small, it is not working properly, right? So there is a requirement, and this is the symbolic notation of this. So it has this 25 volt reference, and this reference voltage, and you should consider AC and DC, but now we are considering AC only because we are dealing with compensation, AC compensation, right? So this AC is coming in, and this is the VK and IK. This maybe this is the DC, and the AC is reflected to here. Then this will be DC plus AC. So, but we are only interested in DC. So it is this one, VR AC in, IK AC out. Because of this, it is called transconductance amplifier, and it has good reference. Temperature compensate, the band gap voltage reference, and this is open collector structure. Okay, this is the one simple structure of operational transconductance amplifier. There are many things, many complicated circuit for this. Maybe this is the simplest implementation of that. Okay, and this is the specification of this TL431. This should be open loop transconductance, not voltage gain, because this is the transconductance amplifier. Okay, and this should be small signal voltage amplification is long. Okay, I took this from the book. The guy named Basso, he wrote one book, and I took his data. Maybe he was confused with this. Okay, this is Transconductance amplifier. Okay, so it has this kind of open loop transconductance structure due to the compensation cap. Okay, with this, and the important thing is spec, absolute spec of this VK, cathode voltage, this one, VK, this cathode is AC plus DC. Okay, when it is working, it responds to the AC signal, so it has AC, DC, and DC is required for the bias, so IK and VK, there is an absolute minimum. It should be larger than 2.5, which is this value. And this one, IK, should be absolute minimum, which is 1 milliamp. Maximum is 100 milliamp. Maximum is 36 volt. So the safe way is use much larger than this. Maybe 10 volt, 5 milliamp, something like that. Don't play around here. Then you are dangerous. Okay? Your converter is not working properly. That's bad. The worst thing is sometimes it's working okay and sometimes not. That's the worst scenario. Okay? All right. So you understand this, right? So when you are thinking about this amplifier, think about the AC and DC separately. Otherwise, you got confused. Okay? Symbol of TL431. Okay, so this one is exact circuit diagram, and this is the symbol I am using. So I flipped this horizontally. Okay, then there is an inverting function. So I used this inverting function. This is not an inverter, inverting functionality, and this one with this sign changes. Okay, so this is a normal sign we are using. This becomes R, becomes inverting terminal. This becomes non-inverting terminal. This is swapped because of this. Okay, so I'm using this in my textbook. The book I wrote, I'm using this, and some people using this. This is very strange signal. This is Gino amplifier. And in the middle of Gino, there is just some terminal is coming out horizontally and called R. Okay, so this means this. Okay, and many people think this is the Gino diode. Okay, so some people say TL431 is Gino diode. There is one application. If you connect in this manner, then R and K are connected. Then it becomes unique gain buffer. Then that is the same as this one. Okay? Because this is one voltage source, which is the Gino diode, like behavior. It shows Gino diode like behavior. Then they think this is the Gino diode. They connect together and use it as a Gino diode. That is fine because this characteristic is very good. And sometimes the price of this is cheaper than Gino diode. That means this IC is so popular, so best produced, the price is just lower than simple diode, which is good, okay, for us, right? But don't use this way, okay? So it has something more than that. Okay, so let me discuss this in relation to our application. Okay, so this is an isolated 2.10 compensation. So it is structured in this manner. This is TL431, and this is the optocoupler or photocoupler. Okay, and this is the this bias voltage, and this RC, and the voltage here is control voltage. This is PWM block. Okay, it really doesn't matter whether it is voltage mode control or current mode control. Okay, so this remains the same. The current mode control, this waveform has more than this ramp signal. It has some extra signal sensed from the switch current. Okay, but functionality of this voltage, this voltage remain the same. So it really doesn't matter whether it is current mode control or voltage mode control. Okay, think about this. This is output of your compensation. So for some reason, output of compensation exceed the desired value, some unknown reason. So this one is increasing. Then you have negative sign here. This means this one is increasing. This one is decreasing. Okay, there is the meaning of this inverting terminal here. If this voltage is increased because of this current is increased, this increase, then this decrease, then this ID is increasing for two reasons. This becomes smaller. That is one reason. Another reason is this becomes larger. So it is increased twice. So this is increased. Then IT is increased, not this direction. IT, this is increased or decreased. It does not indicate the direction. So this is increased. Then this voltage drop is increased. Then V cone is decreased. Okay. First, this one is PWM signal. Original PWM signal with V cone in purple. So duty ratio was this much. And this one is red curve with V cone prime is this one. Then this becomes smaller. So duty ratio is reduced. Then output voltage will be reduced. This is what? This is negative feedback. Okay. There is a built-in mechanism. If something goes in the wrong direction, this mechanism is fixing that. That is the nature of negative feedback. So this should be works. Okay. If you swap this sign somewhere or direction of the current, then you have positive feedback. It don't work. Okay. So this is work. Okay. Then output regulation. This is our voltage, and obviously we have, because of this capacitor, we have integrator structure. If there is an integrator structure, there is a virtual short appearing here. That means our voltage divided by this DC current is not going through this. Okay. Then this divided by 2 resistors should be same as this virtual short. So you have this. Then our voltage is, this reference is 2.5. So 2.5 times 1 plus something else. So our voltage should be larger than 2.5. That depends on ratio of this. Okay, this. In the next lecture, we'll derive this. The proof is coming later. In the next lecture, we'll derive this. It's very simple. Okay, is some circuit analysis or electronic circuit analysis. Very simple. Some children's play, actually. Very simple one. Okay. Based on that result, the structure of this is this one. So we have minus sign here because we have negative feedback eventually here. And we have this is integrator, and this 1 pole, and this 1 0. So this is the 2 pole 1 0 compensation. Never call it as type 2 something. Okay, that is very stupid naming. All right, and problem here is this is the expression of KV and omega GC and omega PC, right? We have 2 problems here because this is, it has some tolerance. Okay, there is some uncertainty here. So KB will move around depending on CTR of actual device. Okay, with some tolerance, of course. And another one is RD. RD is here, but RD is related with bias voltage to here. Okay, later on I'll show you some simplification. So RD is involved with the bias voltage of this one, bias voltage of this circuit. So some limitation here. So you cannot control this. There is another problem. For some case, the IC, using NCP 1230 has this thing is inside of the IC. Okay, inside the IC. You cannot change this. Then this is the fixed, right? So you cannot change. This is a bad thing for the designer. Okay, you are losing one freedom. Okay, that's a bad thing. This one is okay. You can play with this. And another one is this pole is determined by this, and this one is fixed by this IC designer, and the CJ is there's uncertainty here. Okay, so there's just some tolerance here. Okay, so this is the one type of possible configuration of this structure using this TL431 and optocoupler. This is called the common emitter configuration. I don't know why. There's another configuration, many other configurations, but this one is most popular. Okay. The Basso guy, I told you his name several times. Okay, he is French. Okay, and he has all of this tedious stories. Okay, if you have more time you necessary, then read his book. Otherwise, you don't have to read his book. Okay, Basso's book. Somehow that book is very popular. I don't know why. Okay, and this one is the same thing. I summarized. Okay, for the discussions we went through, VT. This voltage, VT. This voltage is VT. Prefixed, and this control voltage is prefixed. Okay, then this IT is fixed. Then due to the vendor supplied the curve, you find out the operating point, and ID is fixed. Okay, then you need to check this ID, this one, DC value of this one should be sufficiently larger than 1 milliamp. And this voltage here, which is this one minus voltage drop here, and minus this diode voltage, which is very close to the 1, then that voltage should be much larger than 2.5 for the proper biasing of TL431. Okay. In the past, I consulted with some company, LG company, and they said they have some problem with this optocoupler, this TL. Then this current was slightly smaller than this, and this voltage is 1 point something. Okay, then they don't know why. Okay, so that is very dangerous, bad design. Okay, sometimes okay, sometimes it's not working. That is the real problem for them. Okay, so you should know this. Okay, that was very stupid mistake. Okay? But then you should know these simple things. And this curve, I took this graph from Basso's book, and what he wants to say is this is the relationship of VM and IK. And this one is transconductance amplifier. So if V1 is increasing, this K is increasing, IK is increasing, and this curve is something like this. And the GM in here is very large. GM in here, GM means it's a slope. Okay, slope at operating point is small. So to have this large GM about this value, okay, then you should IK should be this one, no. If IK is smaller than 1 milliamp, this is a 0.6 milliamp, and then you are in trouble. Okay, this is obvious. Okay, there's no energy source in TL431. You should provide something. You should work. You should eat to work. Okay, that principle. Right? And bias current condition, this is important. So for some reason, this current is smaller than 1 milliamp due to some distraction. Then you add this RB, okay? Then RB is carrying current. That current is not coming from here. That current is coming from this. This works as the voltage source, 1 volt. And this resistance, this 1 volt divided by this RB is current is coming here, and current cannot go this direction. Then current is here, okay? So you are providing some additional current, I bias, okay? So IT is VT divided by V con is fixed, IT. Then ID is IT divided by CTR. This ID is coming from here, okay? Then this one is not large enough. Then the voltage drop here is 1 volt. And using that, you are generating additional current, I bias. Then this will provide the current much larger than 1 milliamp. Okay, that's the trick. Right? This is very important. Okay. Then this RB should be small, much smaller than this. RB is order of 100 ohm, 200 ohm, something like that. If this is the 50 ohm, then that's nothing. Okay. It ignores in small signal analysis, so you don't have to consider this resistance or this resistance. You are assuming this RD is dominating everything. Okay, but there is some additional current, auxiliary current coming from diode to boost the bias current of this. Okay, so that is written here. Impact of this is large, okay? No. I bias is not sufficient enough to provide the bias current here, okay? Then this becomes, as I said previously, this becomes 2-pole 1-0 compensation, okay? I'm not talking about the open loop transconductance of this. I'm talking about the transfer function from here to there. Okay, this is also transconductance because input is voltage and output is current. Okay, and when so the regular 2-pole 1-0, you have 1 pole at the origin integrator. You have 0 here. You have another pole. Okay, if I bias is 1.3 milliamp, you have this curve, okay? But if I bias is not sufficiently larger than this one, for example, 0.3 milliamp, you have this, okay? So this region is different. This is another 2-pole 1-0 compensation. Integration is not working here. Then you don't have good output regulation. You cannot regulate our voltage at 2.5 with this. To regulate our voltage at the 2.5 volt, this should have this slope forever, okay? But this is saturated, right? So it causes problem, bias of this, and it also problem, functionality of 2-pole 1-0 circuit, okay? So RB, and RB is much larger than RD. The small signal characteristic of this compensation circuit remains unaltered. This is the final discussion about this. This is typical example of this flyback converter. Okay, initially they are missing. This is missing. Okay, so this is connected, and there is only one capacitor here. Then that case, this is our voltage. So our voltage has large this ripple, and it has large spike, 280 millivolt, 0.2 volt, about 0.2 volt spike. Okay, so this is very bad. Okay, you should reduce this. All right. So this causes the EMI problem, and output is not a DC anymore. So this is huge spike, and just adding this one and this one, very small one, you have 2-stage filter, and with that, this our voltage is changed from here to here. peak to peak value of this, including this switching spike, is this about 1/10 of this. Okay, so this is dramatic improvement of using two-stage out filter. This is a flyback converter. So there is a filter. This is the magnetizing filter, magnetizing inductance of this flyback transformer LM. You are not seeing this. This is the inside of this transformer. But this works as the inductor, functional inductor in other converters. So assume this is an inductor, and this is the extra element, extra component you added. Okay, this should be very small, smaller than this magnetizing inductance of LM. Okay, sometimes if you use some long wire, there is this LF. Okay, so LF is already there. Okay, you can make use of it. Otherwise, it works as the noise source. But if you make use of it, you are using two-stage filter to knock out this spike and this ripple component. Okay, and there is one extra capacitor here, and this is the original capacitor used in original flyback converter. So original flyback converter, you have a capacitor here. This is the new one. Okay, you add small inductance here, and the small capacitor at this part, at this port. Okay, before this. Okay, in terms of the circuit property, it really doesn't matter whether this comes first and this comes last, or vice versa. In this soda, transfer function remains the same. Transfer function is not dependent on the order of component, okay? But the benefit of using this is if the small capacitor is here, larger one is here, you have same waveforms, but somehow you have some parasitic capacitance connected here. There is some capacitance, parasitic capacitance. Then parasitic capacitor will be merged with this, then it will disappear. Because this one is very large, so that the parasitic capacitance does not change any circuit operation. But if this smaller one comes to here, then this is the design value. Design value will increase twice, 3 times, something like that. That's bad. Okay? So for this purpose, to provide the robustness in this configuration, it is proposed to place this at the end of your converter. Okay? Most people, they use bigger one, front, smaller one at the end, which is the bad choice. Okay, understand this? All right. Okay, and this photo is taken from the Lidri. Lidri's, you know the Lidri, guy named Lidri. He was my colleague. Okay, when I was studying. He proposed this second stage filter. Many people are using this without analysis, but there is one problem with this, because then power stage becomes false order. You should deal with false order system, and he proposed a systematic way of dealing with that. The trick is the second resonance. There are two resonances, separate them, and kick out the second one out of the band. Okay, that is the trick. All right, and this will provide good things in your design. Okay, and we are seeing this dramatic change in the quality of our voltage with very small reactive component. Okay. Okay. So this is about the optocoupler and operational transconductance amplifier. In the next lecture, we'll discuss the optocoupler isolate feedback circuit for the peak current control, the analysis and the design of 2410 circuit using this TL431 and optocoupler. And then we'll move to the dynamic analysis of this flyback converter and the design of current mode control and the functional, the evaluation of performance of this converter using PSIM simulator and the improvement and so on, right? Okay. All right, okay. Thank you. We stop here.